The formula for momentum is P equals mass times velocity. Because velocity is a vector, so is momentum. Momentum will always follow the direction of the velocity. And in the global SI system, momentum is measured in kilograms times meters per second. It doesn't have a special name like watts or joules. And because it's connected to mass, that means the more mass, the more momentum. For example, let's say you had two baseballs and they're traveling in the same direction. One's going at this speed, one's going at this speed. Which one's got momentum more, the faster one? What if you had two airplanes and this one here is heavier than this one here? Which one has more momentum if they're traveling at the same speed? It's the heavier one. Because of Newton's laws, to change the momentum of an object, a force is required. Some kind of force in some way. Newton's second law was actually originally stated in terms of momentum. We all know it as F equals ma. But when Newton first wrote it, it was F equals the change in momentum over the change in time. So this means that the rate of change for momentum, the speed at which it changes, is equal to the net force being applied on whatever object you're talking about. Now, before we go into examples and problem solving, for fun, I'll show you how we derive the normal version of Newton's second law from this. So it's F equals the rate at which momentum changes. And momentum is mass times velocity, right? So we can write the change in momentum as the final mass velocity minus the initial mass velocity divided by change in time. Factor out mass because mass is constant here. You get mass times the change in velocity divided by change in time. This is also written as mass times delta velocity, delta time. And what is this? If you notice, this is the formula for acceleration. So you get mass times acceleration. F equals ma. Let's go through a problem. Imagine for a second you're a pro baseball athlete. This is you. And baseball people wear hats, so you have a hat. You hit a ball with a bat, and when the ball, after being hit, just leaves contact with the bat, it's hit at 50 meters per second. The ball itself is 150 grams. And let's say the ball is in contact with your bat for 3 milliseconds. What's the average force on the ball? Okay, first we have to do some unit conversion. 150 grams is 0.150 kilograms, and 3 milliseconds is 3 times 10 to the power of negative 3 normal seconds, which is 0.03 seconds. And what are we looking for? We're looking for the force on this ball. And we have the mass and the velocity. So let's use our new formula. Change in momentum divided by change in time. Change in momentum would be the final momentum. So the momentum just after ball leaves contact with the bat. Minus the ball at the start, which is when it gets hit. Divided by the change in time, which is this many seconds. That's how long it's in contact with the bat. If you go and plug in your values, then you get roughly 2,500 newtons of force. And we say roughly because we're neglecting gravity. If you went and solved for how much force gravity is doing on this ball, it would be a very small number, so we don't have to consider it at all, especially since the time interval is so small. So you smack the ball with this much force, and that's a lot of force, 2,500 newtons. For reference, to lift up a 60 kilo human, it's only about 600 to 800 newtons of force required. Let's go through another problem. Imagine for a second that you're a firefighter, and there's burning buildings on fire because it's burning, and from your awesome fire truck, there's a hose, and you use this hose to shoot water at this fire. The water is shot out horizontally at 15 kilograms per second with a speed of 30 meters per second. Assuming the water is stopped completely when it hits the wall, without splashing back, what's the force the water is exerting on the wall? We can do a similar thing to the last problem. We're looking for force, just momentum over time. But here's where we have to do a bit of thinking. Change of momentum is the final momentum minus the initial momentum. What's the final momentum? The final momentum is 0 because the water gets stopped. Well, what's the initial momentum? We know that momentum is mass times velocity, but we're not given an explicit, we're only given this, the fact that every second that passes, 15 kilos of water leaves the hose. So let's use this as our time interval, 1 second, and this as our mass. 15 kilos per second multiplied by the velocity, 30 meters per second, divided by our time interval, which is 1 second. And this is equal to 450 newtons when we neglect gravity. When we assume that the effects of gravity are negligible. If you have any kind of system with stuff going on, if no net force acts on this system, the total momentum inside the system will stay the same, which means that the momentum inside is a conserved amount. It doesn't decrease, it doesn't increase. What does that mean? Let's take an example. Imagine 2 ice skaters. So this is ice skater 1. We'll label him A. And this is ice skater 2. We'll label him B. And they're wearing ice skating shoes because they're ice skating. Let's say they're very clumsy and they bump into each other and they collide. Their individual momentum will change. They'll slow down and go in a different direction after bumping into each other. However, in total, the sum of their momentums, the P of A plus P of B, stays the same after this collision. And so let's set up some math that we'll use in this video. The total momentum before the collision is the vector sum of both of their momentum. So that would be mass of A times velocity of A plus the mass of B times the velocity of B, because that's the momentum formula, right? And that's the total momentum in this system before the collision. After this collision, this horrible tragedy, they now have a changed velocity and direction. So their momentum is different. The momentum of guy A after the collision, we will denote with this symbol. This is called priming the quantity. So it's denoted with a prime. And this is simple. And really, it's just a label. It means this, but after the collision. And we'll do the same thing for the second dude. His momentum after the collision. Following the collision, the total momentum in the system is the same as it was prior to the collision, because there's no net force acting on them. It's just these 2 guys. And this right here is the equation for the conservation of momentum. Before we solve problems, let me explain another concept for you. Newton's third law guarantees that inside an isolated system, what's an isolated system? Well, it's the set of objects that we choose. For example, the 2 ice skaters. Inside an isolated system, internal forces will cancel. What does that mean? All you have to worry about is that inside an isolated system, momentum will be constant, like we just discussed. But only when there's no external forces. But what if there is an external force? Then momentum wouldn't be conserved anymore, right? It would change unless you redefine your system. Let me explain this to you. Imagine you throw a ball into the air, and then the ball on the way up will slowly slow down because of gravity, and then it'll speed up. The momentum of this ball specifically is changing. It's low up here, and then it's higher on the way down. The total momentum in this system is not constant because there's the external force of Earth's gravity. But if you redefine your system as the ball plus Earth, then the total momentum is conserved, because as the ball goes up, Earth actually goes down by the tiniest amount, which means that in total the momentum balances, it stays constant, but only because we included Earth in our system. Now here's a note: the conservation of momentum is more fundamental than Newton's laws. Even when Newton's laws fails at the atomic level, conservation laws of energy still hold, especially for momentum, so it's more universal. Here's a proper example now. You have two people playing hockey. This is person A, and this is person B. And person B is shocked because person A is flying toward person B at 7 meters per second. Person A is 90 kilos and person B is 70 kilos. After this collision, they grab onto each other and slide off together. What's the final speed after this collision? Okay, let's set up our problem. Because of the conservation of momentum, we know that the total momentum before is equal to the total momentum after. The total momentum in this system before is the momentum of dude number A, which is the mass of A times the velocity of A, 90 kilos times 7 meters per second. And it's equal to the momentum in the system after. The total momentum in this system prior to the collision is the momentum of dude number A plus the momentum of dude number B. Momentum of dude A is 90 kilos multiplied by 7 meters per second. And dude number B, he has a mass of 70 kilos, but he's at rest, so his momentum is 0. We just won't write that. But because they stick together after colliding, grab onto each other, and slide off together into the sunset, then we will consider their mass as 1. So mass A plus mass B multiplied by their velocity. And this velocity will denote with a prime to state the velocity after, because we don't want to get it mixed up with this velocity initially. Let's do the math. This is 630, and it's equal to their total combined mass, which is 160, multiplied by their final velocity. Divide both sides by 160 so that we can isolate the final velocity, by the way, is what we're looking for. Then we get final velocity is somewhere around 3.7 meters per second. So after they collide and stick together, slide off, this is how fast they're going. And we had to use the conservation of momentum instead of things like the kinematic equations, because there's two objects and they stick together after. So it's a little bit more complicated, and the conservation of momentum gives us the answer perfectly. Here's the second problem. You have a cannon. Here's our cannon. It's got a wheel, fuse. Anyway, the cannon is 2,000 kilos. And the cannonball that it fires is 20 kilos. It's initially fired horizontally at 250 meters per second. The cannon itself is initially at rest, and if we don't consider friction, what is the recoil speed after it fires this cannonball? Let's break this problem down. So first, let's identify what we're given. We have the mass of the cannon, 2,000 kilos. We also have the mass of the cannonball, which we'll label with B for ball, 20 kilos. We have the velocity of the ball initially, 250 meters per second. And we also have the total momentum initially, which is 0. Why is it 0? The ball hasn't been fired yet, so 0. And here we have to use the conservation of momentum because there's things moving back and forth and things are being balanced by each other, like the recoil, which is based on how hard the cannonball is being fired. Because momentum is always conserved inside an isolated system with no net forces, then we have to use the conservation of momentum to find the correct answer. Let's solve. So we know that the total momentum inside this system is the momentum of the cannon plus the momentum of the ball. And initially, it's equal to 0. The total momentum in the system before firing the ball is the momentum of the cannon plus the momentum of the ball. And initially, it's 0. Now, what are we looking for? We're looking for the cannon's recoil velocity, right? And that's this value right here. So let's move this to its own side. Mass of the ball plus mass of the velocity. Momentum of the ball is equal to the negative momentum of the cannon. Now we will divide by mass of the cannon to fully isolate the velocity of the cannon. And you get this equation right here. So now we've set up an equation where we can solve for this. And we got this from the momentum of conservation equation. By the way, there's a lot of formulas like this going on here. And there's a free cheat sheet I made for myself in the description if you want it. Plug in our values because we know everything here, right? Then you get the answer as negative 2.5 meters per second for the recoil speed after firing the cannonball. This is a small amount, but remember that the cannon is 2,000 kilos. And it has recoil speed because momentum needs to stay balanced. It can't just fire the ball and stay completely still. Collisions happen every day. For example, when you stub your toe, when you slap a fly, or when you're playing pool. When we solve problems involving these collisions, the time interval is so short that external forces like friction and gravity don't really get the chance to do anything. For example, when you punch someone in the face, for the short amount of time that your fist is in contact, you can ignore the friction that comes from your hand rubbing on their face, and you also can ignore the force of gravity pulling your fist down. Because you're only in contact for so short time. Now what's impulse? Remember Newton's second law in terms of momentum is the net force being applied is the rate that momentum changes, which is this formula right here. Let's multiply both sides by t, and we get this. Change in momentum is equal to force times change in time. The force multiplied by the time interval is equal to impulse. So the impulse is the total change in momentum during this short time interval. On a graph, it would look like this. Let's say this is our very short time interval. This is the time in which the collision happens. And this means force. It'll go up and then it'll go right back down. And the average force during this collision, don't worry, this is all going to make sense soon. The average force would be something like this. And underneath this area, the shaded area, that is your impulse. But this would need advanced math like calculus. So to approximate this changing force, we're going to use an average force. Let's go through a real example. A Kung Fu master, so this is him, he has his Kung Fu beard. He has a brick in front of him. And to prove his Kung Fu strength and his skill, he smashes his head into the brick and it breaks in half. He smashes his head into the brick at 20 meters per second. Let's find the impulse. Force multiplied by time is equal to change in momentum, as we just discussed. Momentum is mass times velocity. So the change in momentum would be mass times the change in velocity, because mass doesn't change. Let's say his head is roughly 5 kilos. That's the object we're working with. Which means that the mass is 5 kilos and the change in velocity is 0 to 20 meters per second. So 20 meters per second. This is equal to 100 kilos times meters per second, which is a weird unit of measurement, but if you remember, That's how momentum is measured. Let's say that the time his head is in contact with the brick is 3 meters per second. That's our time interval. Now, what was the point of finding this? Let's say we wanted to find the force his head is exerting on this brick when he breaks it. Okay, the force formula with momentum is change in momentum over change in time. And we need the time interval. Let's give a rough estimate. Let's say 3 milliseconds. 0.003 seconds, that means. And this is 50,000 newtons, which shows just how good at Kung Fu he is to shatter this brick. So impulse is a pretty abstract concept. But in most physics textbooks and physics courses, you will see impulse denoted with J. In most collisions of two objects, we don't know how much the force changes during this super short time interval. So if we try to solve for values and we use Newton's second law, it gets messy. So instead, we rely on the conservation laws. When there's no external forces acting on a system, then momentum is always conserved. Now let me define something for you. It's called an elastic collision. In perfectly elastic collisions, kinetic energy is always conserved as well. What does that mean? A perfectly elastic collision would mean that there was no kinetic energy loss. So no kinetic energy was turned into heat from friction. No kinetic energy was lost as sound. And this type of collision is nearly impossible in real life. And even though during this super short collision, the kinetic energy can actually turn into elastic potential energy because the objects get compressed slightly. So some of the kinetic energy will turn into elastic potential energy before they bounce off each other. So if you compare the kinetic energy in this system before the collision compared to the kinetic energy after, they are the same because it's conserved. And when this is the case, the collision is elastic. And even when the collision is inelastic, total kinetic energy may not be conserved, but total energy always is. Because some kinetic energy might turn into sound or heat, but in total, the energy doesn't change. That's a law of the conservation of energy, which is universal. The conservation of kinetic energy in equation form is this, and don't worry about this. This is simply kinetic energy of two objects before versus after. And this is a really fat equation. But there's a shortcut one that we can derive from this, and I'm not going to go through the derivation. But the equation that you get, that velocity of object A minus velocity of object B is equal to velocity of object B minus velocity of object A after the collision, which we label by priming the quantities with these symbols. This is what we discovered in relative velocity all the way back in 2D kinematics. Another form of this equation is velocity of A minus velocity of B is equal to minus velocity A after minus velocity of B after. This is interesting. That means the relative speed of the two objects are the same regardless of mass, even though it's in an opposite direction. This shortcut equation, when it's applicable, it's much easier than this big fat equation up here because velocity is not squared. That was a lot of math. So let's go through an example to connect this to physics and real life. On a super slippery ice surface, you have two hockey pucks. This is hockey puck A, this is hockey puck B. They have the same mass. B is initially at rest, but A is flying at B with a certain velocity. Following this collision, what is both of their velocities? Okay, let's break this down and set up our problem solving. So these are the two unknowns. These are what we're looking for. Before every energy conservation kind of problem, we have to see what's conserved. Let's just say there's no friction because we're on ice. That means momentum is always conserved. Let's say this is an elastic collision and there's no friction. What is conserved? Well, there's no external forces because even gravity doesn't count because the normal force cancels it out. So momentum is going to be conserved. kinetic energy is also conserved because this is an elastic collision. And since the masses are equal, then we get to use our special shortcut equation. And we use this because it involves the two unknowns we're looking for. But we can't just go ahead and solve it. When we have two unknowns, we need two independent equations to solve for it. That's like simultaneous equations. So let's get a second equation in here that has the same unknowns. And that second equation is velocity of A plus velocity of B is equal to the velocity of A after and the velocity of B after. Where did we pull this equation from? It doesn't come out of thin air. This is the conservation of kinetic energy, because kinetic energy at the start is equal to kinetic energy after. And we can use that because kinetic energy is conserved in an elastic collision. So now that we have two equations, we can solve for our two unknowns. Let's add these two equations to each other. When you add these two, you get 2VA. Add these two, they cancel out. Now what about the right-hand side of the equation? Let's add the like terms. When you add velocity B to velocity B, 2 velocity B. When you add this velocity A to this velocity A, since it's negative and positive, they cancel out. So we're left with this. Cancel out the 2's, you get velocity A is equal to velocity B after the collision. And why did we choose to add? It actually doesn't matter, because if you subtracted these two equations, you would get this equation. It's very similar. Let's actually use that equation. We know that velocity B is 0, which means that the velocity of the puck A after the collision, it stops. And the initial velocity of this puck is how fast puck B moves after the collision. So they basically swapped speeds. Puck A went from VA to 0, and puck B went from 0 to VA. The energy was transferred, and the total kinetic energy and momentum stays the same. This was a very math-heavy example with no real numbers, a lot of algebra, and you might have gotten a little lost along the way, so let's do a real-life example. So let's go through an example with numbers. Imagine the inside of a particle accelerator, like the super colliders, and a proton inside. Let's draw it like that. It's launched toward a stationary helium nucleus at this speed, which is very fast, but that's how things work inside particle accelerators. The collision is head-on and is perfectly elastic. After the impact, what are the final velocities? And let's say the mass of the proton is equal to 1 atomic mass unit, and the mass of the helium nucleus is 4 atomic mass units. Let's see what we're given before solving the problem. We're given the mass of these two things, of these two particles. And we're also given their velocities initially. The helium nucleus is moving at 0 meters per second, is at rest, stationary. The velocity of the proton, as we know, is this big number here. We're looking for the velocity of the helium nucleus after. Because momentum is conserved, then we can use the conservation of momentum, which says that the momentum of the proton plus the momentum of the helium, which is the total momentum in the system, is equal to the total momentum after. To solve for these values, we need a formula. So let's use the elastic collision formula from last video. And all these formulas, it's very hard to remember them all. So I make a cheat sheet for myself, which you can get for free in the description. And you can choose whatever topic you want. The momentum of the helium particle is 0 because it's stationary, which means that we don't have to consider this. Our equation is simplified to this. Now, where would you take this after? Keep in mind, this is what we're looking for. Let's use that shortcut formula. And here we have the velocity of the proton initially. And here's our two missing values. That's what we're looking for. Okay, we need at least one of them to find the other. So let's find the velocity of the proton after. If we rearrange this equation for this value, we get this. We can substitute this in right here. And why would we substitute it into this equation? It's the same thing because we have two unknowns, but only one equation. And we need a second equation. And we have an opportunity here. We can solve for this. So let's move everything to the other side. And we end up with this formula. The velocity for the helium nucleus after the collision is 2 mpvp over mp plus mhe. And this is another formula in the cheat sheet because this pops up occasionally. Plug in your values, so the mass of the proton is 1, and then this velocity of the proton. Plug in your other masses, and it's messy, but we get this value. That's how fast the helium nucleus moves after the collision. Now what about the velocity of the proton after the collision? Let's use our formula right here, because that's exactly what it solves for. So velocity of the proton after the collision is this minus the initial velocity, which we already knew from the start. That gives you this, negative 3.6 times 10 to the 5 meters per second. If you noticed, when you put these two together, you get this. The initial velocity of the proton before the collision. So after the collision, there's the same total kinetic energy and momentum. However, it's just been split between these two particles. And because this is negative, that means the proton bounces backwards after the collision, while the helium nucleus gets pushed forward. That makes sense because this proton is quite light compared to the helium. The helium is 4 times heavier. This was a lot of math, and you might be kind of confused on the decision making when it comes to formulas and substitution. But practice makes perfect, and when you practice enough, this becomes natural. If you're interested, go follow me on Instagram. When two objects collide, if the kinetic energy is not conserved, so some of the initial kinetic energy the two objects had turns into sound or heat, and the total kinetic energy is lost, then the collision is inelastic, since kinetic energy before and after the collision is different. There's two main types of inelastic collisions. The first type we call partially inelastic collisions. So the objects bounce off each other after the collision, and they lose some kinetic energy. The second type is completely inelastic. And in these cases, the objects stick together and they slide off together. And that's maximum kinetic energy loss. When it comes to inelastic collisions, key laws still hold. So of course, momentum's always conserved, and total energy, so all forms of energy, is also conserved always. But there is a special case, and that's explosions. So let's say something explodes. Potential energy in the form of chemical or nuclear energy gets released as kinetic energy, and the total kinetic energy after the explosion is actually greater. Now in real life, most everyday collisions, like people bumping into each other or a ball bouncing, are inelastic. It's very, very, very rare for a perfectly elastic collision to happen outside of physics experiments. Okay, we just talked about a lot of energy stuff. Let's apply it to a problem so you can understand it. The problem is, there's a hanging wooden block. And this wooden block, you throw a dart at it. Now this dart, when it hits the block, it sticks inside of it. And then it gets pushed and swings up, like this. As it swings up, it's going to reach a max height and then come back down. This max height value, related to the initial velocity of the dart, is what we're going to try and find. So let's do some labeling before we set up the problem. This mass of the dart will be m. Mass of the block will be big M. Velocity of the dart will be v. You might have noticed I haven't given any real numbers for this problem. In a lot of advanced physics, what most people will do is they'll solve for variables first. They make equations relating variables to other variables, and then they plug in numbers. So when it comes to pure solving, the ability to rearrange things and find specific values is the important part, because plugging in values is easy. You can use a calculator to plug in values. So here's our approach. We're looking for some kind of equation that relates v to max height. Whatever this might be, right? And because these objects stick together after the collision, that means it's completely inelastic. Kinetic energy is not conserved, but momentum, as always, is conserved. So let's say phase 1 of the problem. We will look at the short time they collide, the short collision time, where momentum's conserved but kinetic energy is not. Phase 2 will look at what happens after the collision. So what happens from here until they swing up to max height. Now, kinetic energy is not conserved, right? It's lost, but lost as what? Kinetic energy after the collision transforms into gravitational potential energy as it swings. So that means we get to use the conservation of mechanical energy. Phase 1, we're going to be using the conservation of momentum. Now, why this phase 1 and phase 2? Because there's two main events, the collision and the swing, which is what we cover here. Let's make some space. Phase 1. Because momentum's conserved, the total momentum before and after is the same. What's the total momentum before? There's the momentum of the dart and the momentum of the block, which is 0. Because it's stationary, so we just won't write that. And the momentum after, since the objects stick together, it would be their combined mass multiplied by velocity primed, which just means the velocity after the collision. And we prime it because we want to clearly separate it from the initial velocity. They're different. Let's solve for this value right here. The velocity after is equal to mass times velocity divided by the combined mass. Cool. That's phase 1 done. Let's now solve for phase 2. Mechanical energy is kinetic energy plus potential energy. Kinetic energy is equal to 1/2 mass times velocity squared. And in this case, because the time interval we're using is after they stick together, it would be their combined mass. Yeah? If you look at the kinematic equations, velocity squared is 2 times acceleration times displacement. Acceleration here is acceleration due to gravity, and displacement is the max height, times 2. And if you plug this in to kinetic energy, let's do that really quick. Then this cancels out and you get this simplified version. Combined mass is multiplied by gravity times height. And that's your kinetic energy. Now, why do we do this? Let me explain the reasoning. This here doesn't do anything, this normal kinetic equation. It doesn't help us solve for what we're looking for. So we had to find a way to put it into terms where it relates to our actual problem. Now we have kinetic energy. We know that this is velocity squared after the collision. What's our options here now? We have height on one side, but we're trying to relate it to initial velocity. Let's look at what we've done. Do we have initial velocity anywhere? And are we able to insert it on the left side somehow? Because remember, our goal was to relate initial velocity to height in some way, whatever's in between, as long as they are on both sides of the equation. Okay, so we have height on one side, but look back here. Prime velocity we solved for in phase 1. And on the other side of the prime velocity equation, there is initial velocity. So let's plug in this value. Mass over combined mass multiplied by initial velocity is combined mass times gravity times max height. And remember, this is squared, this value, because of that. So if we go ahead and rearrange this equation for initial velocity, we get velocity equals mass plus big mass over small mass multiplied by 2gh. There we go. We've gone and related initial velocity to maximum height. And I've tried to make this as clear as possible, but it's difficult because these choices in equations, choices in formulas, and rearranging is a skill that you need to develop, and that only comes with practice. Here's a second example, and this one's not as math heavy. So imagine we're in deep space, and there's a space station. And this space station is stationary relative to Earth. Okay, it's just floating there. It's not really moving. And we launched a supply module that we're trying to dock onto this spaceship. So we're trying to attach it to it. This module is flying through empty space at a velocity of 0.75 meters per second. The supply module is 5,000 kilos, and the space station is 95,000 kilos. After the gentle docking, so they're attached together, they become one object and continue moving after the collision. So the problem is, solve for two values. The final velocity after this collision and the kinetic energy lost during the docking process. Okay, here's our approach. Because the two objects completely stick together, it's completely inelastic, which means that kinetic energy is not conserved. But as always, momentum is conserved. So before is equal to after when it comes to momentum. Let's look at before. What's the momentum before? We have mass times velocity. Let's look at after. What happens after? Well, the new mass of our space station is the mass of the supply module plus the mass of the big space station. The speed is whatever the speed is after the collision. That's what we're looking for in question A. And the reason why the before momentum is only the momentum of the supply module is because the space station is stationary. Now we're ready for some solving. If we go ahead and rearrange for this value, we get primed velocity is equal to momentum of the supply module and the combined mass. If you plug in our values, so what's the mass of the supply module? 5,000 kilos. The velocity, 0.75 meters per second divided by the combined mass, which is 5,000 kilos plus 95,000 kilos. The answer is 0.0375 meters per second. So after they collide and stick together, they float as one object at this speed, which is a lot slower than initially, but that makes sense because when they collide and stick together, the space station is very heavy, so it will slow down. Okay, what about question 2? The lost kinetic energy. The lost energy would be the change in kinetic energy. So the difference between the kinetic energy at the start versus the kinetic energy after collision. The difference. Let's find the initial kinetic energy. So initial kinetic energy, we'll use the formula. And we're using the mass and velocity of our supply module. Since the space station is at rest, there is no kinetic energy for the space station. Kinetic energy 1 is equal to 1,406.25 joules after plugging in our values. Okay, cool. Now we need our second kinetic energy after the docking. So kinetic energy 2 is equal to 1/2 combined mass times the velocity afterwards squared. This is 1/2 times 100,000 kilos multiplied by the value we found in question A, the final velocity squared. This gives you 70.3125 joules of energy after the collision. That's a lot less kinetic energy. than there was at the start. 1,400 minus 70, and there's roughly 1,335 joules of kinetic energy lost during the docking process, which is why it slows down so much. This is a video on how to solve 2D collisions. Let me introduce to you how these problems work. So if you have a billiard ball A and it's moving at momentum P, let's say it crashes into billiard ball B, but the collision's not head-on, so they fly off at different angles, with A flying off this way and B flying off this way with their own angles. Because momentum is a vector and momentum is conserved, the x components and the y components of momentum are also conserved. Now, the conservation of momentum says that the total momentum before is the same as the total momentum after. Let's apply this to the x component. So the total momentum before would be the momentum x component of A, which is this, plus the momentum x component of B, which is nothing since it's at rest at the start. This would be equal to the x component of ball A after the collision. So we'll denote that with a prime, like that. That is this part of the momentum vector, plus the same thing for B, which would be this. Since this is at rest initially, we don't have to consider that at all. And let's make some space. Because momentum is mv, then we can rewrite this equation as MAVA equals MAVA of cosine A, which is plus the same thing for B. Now, if you're confused, don't worry. I'm about to explain it all. Let's break this down. So when you break a vector into its x components, you use cosine. All we've done is turn momentum into mv. And then we use cosine. And these are primed quantities, which means the velocity after the collision and the angle after the collision. This is the formula that you use when you apply the conservation of momentum to the x component of a collision. And this is hard to remember. This is a big fat formula, so it's in the cheat sheet I made for free in the description. The y component, we do a similar thing. Initially, the y component is 0 because the ball is going horizontal. So there's no vertical movement yet. That means the left-hand side of the equation is 0. The right-hand side will do the exact same thing as before, but we'll do it with sine, since it's the vertical component. And the two equations that we made right here are the x and y components. Since there's two independent equations, that means we are able to solve for two unknowns. So we can solve for the y component and the x component, and then we can find the path of momentum that our object takes after a collision. Let's put this all into practice with a practice problem. Let's say you have two roller skating girls. You have girl number A. You have girl B. And girls have hair, so let's give them some hair. Girl A moves at velocity of A. Girl B is stationary, and girl A is moving toward girl B. And they collide, they crash into each other. Girl A flies off at an angle of 45 degrees in this direction. Girl B does the same thing, but in the other direction, at the same angle. And this is all relative to the x-axis. So because A is going above and B is going below, then the angle of A after the collision is 45 degrees, but the angle of B after the collision is negative 45 degrees because it's going down. This is our problem. What are their final speeds after this collision? Let's assume there's no external forces on our system, so the conservation of momentum applies. Because there's two unknowns we're looking for, which is the velocity of A, the velocity of B after the collision, that means we need two independent equations, which will be our y component equation and our x component equation. Before we start this problem, I want you to hypothesize what are the girls' speed. My assumption is that they will have the same speed. But in math and science, we cannot assume anything. Let's solve our problem. So let's use the equations that we just created, which by the way are on the cheat sheet in the description for free. I'll quickly write them out. Great, there we go. Since they have equal mass before and after, and because their mass is also the same between each other, let's cancel that. And remember, what are we looking for? These two values. So let's choose one to solve for. Let's isolate the velocity of girl B after the collision for her y component. You can actually choose any of these, but let's use this. Our new y equation after cancelling mass looks like this. Rearrange for velocity B, we get this equation. If you recall from trigonometry and trig identities, then sine negative 45 is equal to negative sine 45. So our equation can be rewritten, simplified, like this. Any number divided by itself is equal to 1. And since it's negative, that means sine 45 over negative sine 45 is equal to negative 1. Which means that our equation is negative VA times negative 1. Which gives us positive VA. So that means our equation is velocity of B is equal to velocity of A after the collision. Which means that yes, their velocities are equal. Our hypothesis is correct. Okay, cool. What about the x component? The x component says that VA equals VA after the collision cosine 45 plus the same thing for girl number B. Now cosine of a negative number is equal to cosine of the positive number, which gives us this. And because VA and VB are equal, we can just write both of these as VA. So this simplifies to 2 times VA cosine 45. We're going to go ahead and solve for this value by moving these two to the other side. From this, we get VA after the collision is equal to initial VA over 2 cosine 45. Now, if we want a real number from this, let's just say the girl was skating initially at 5 meters per second. Then our answer is roughly 3.5 meters per second after the collision. And because VA is equal to VB, this value is also the speed the other girl goes at after the collision. Here's something interesting. On top of these two equations, the x and y equations that we found, if the collision was completely elastic, then kinetic energy is conserved, which means that we would be able to get a third equation to find a third unknown if we had to, which would be the kinetic energy conservation equation. In the past few videos, we've imagined objects in problems as a single point or a single particle, but real objects are extended, right? They're different shapes, things, and they don't just undergo translational motion. They might be rotating at the same time. For example, if someone was doing a backflip on a trampoline. So let me explain to you what the center of mass of an object is. The center of mass is a special point in an object or in a system. And this center of mass, the key property, and we'll label center of mass as Cm. The Cm center of mass moves exactly like a single particle would, under the same net force, even if the object is spinning or breaking apart. What does that mean? Well, the backflip dude, let's say this is our backflip dude. As he flips and spins through the air, he's moving like crazy, right? But his center of mass, it follows a perfect parabolic path while he's spinning and twisting. So here's the mathematical definition which we'll use to solve our problems today. For two particles or two parts of an object, the center of mass is equal to the mass times the position of the first object plus the mass times the position of the second object divided by their combined mass. And this works for as many objects as you want. For example, if you had 5 particles, it will do the same thing, so on and so on. Let's say the masses of the two objects are completely equal, right? The center of mass would be directly midway between the two objects. And two objects doesn't always mean two objects. It could be two parts of an object. So let's say you have a weird shaped object like that. The center of mass, let's say these two have the same mass. The center of mass is directly midway between them. For example, on a seesaw, you have two children of the same mass, then the center of mass is directly between them. Now, what if one of the children was really large? Okay, he's a bit chunky, like that. Well, you know, we're just calling it adult. It's an adult. And his mass is bigger. Where would the center of mass be? It would lean toward the object with more mass, so the seesaw would go up. So the center of mass is closer to the larger mass, but when the masses are equal, it's halfway in between. Here's an example problem. So 3 friends go on a holiday trip and they go on one of those banana boats that you can hire. There's the banana boat, and here's the 3 friends. They are all 60 kilos each. However, their distance from the end of the raft is different. So let's say this is our x-axis. From the left end of the banana boat, friend number 1 is 1 meter away, friend number 2 is 3 meters away, and friend number 3 is 5 meters away. Find the center of mass relative to the left-hand side end. But let's use the formula we just talked about. So center of mass position is the mass times position for each friend divided by their combined mass. This is 60. This is equal to 60 times 1, 60 times 3, 60 times 5, all divided by their total mass. The answer is 3 meters. So the center of mass is 3 meters away from the left end. And this makes sense because the objects are of equal mass. The center of mass would be exactly halfway in between the two ends. What's the difference between the center of mass and the center of gravity? Let's discuss this. So the center of gravity is a single point on an object where the force of gravity is considered to be acting on it. Gravity actually pulls on all particles or parts of an object, but for analyzing translational motion, it's much easier to pretend that all weight acts at the center of gravity. So the center of mass depends on mass distribution and how mass is spread out throughout an object. The center of gravity depends on how gravity acts. So in real life, center of mass and center of gravity are nearly always at the same point. So for translational motion and involving the center of mass, we use Newton's second law. So net force is equal to mass times the acceleration of the center of mass. So big M means combined masses, so sum of all masses. And this is acceleration of the center of mass as it moves along. This is Newton's second law for a system of particles or extended object. And here's an example. It's a conceptual example, not a proper problem, but let's say there's a futuristic cargo drone of 2 bits with 2 parts, part A and part B, and it flies up into the air. But there's a scary flock of birds that attacks it. So an emergency auto separation system launches part B and A apart. Part B flies way forward, like that. But part A gets dropped straight down. What happens to the center of mass? Where does the center of mass go? Okay, if A and B have the same mass, where does the center of mass go? The center of mass, just like the backflip example from the start of the video, it will follow a perfect path as if this separation never happened. It has to be in between A and B to balance it out. Because A gets thrown straight down and B goes way further than it should be, if compared to if they stuck together, center of mass balances that and stays midway. Keeps traveling as if gravity is the only thing and there's no horizontal force.